So imagine an engineering scenario. You've got a pipe, and the pipe's inner wall has been coated with sugar, and you let a fluid pass through the pipe. And what happens is that the sugar that was initially coated on the inner walls of the pipe starts dissolving into the fluid. And so this is a scenario what's called a convective mass transfer. So what's happening is that the flow of the water creates the convection because of which the mass of sugar that was on the wall of the pipe initially gets transferred into the fluid. So in a situation like this, for example, you want to understand how the different variables that are coming into play in this particular situation form a relationship. So, in any kind of experiment, what we normally like to do is we like to gather the variables and we like to fix all the variables except one, and we vary that one variable a couple of times and try to see how this one variable affects the entire experiment. Now, this way of finding a correlation in an experiment is pretty common and it's very effective at times too. But as soon as we start talking about uh, a lot of variables, for example, more than four or five, doing something like this by that method becomes extremely complicated because you have to conduct that experiment so many times, and the more variables there are, exponentially more you have to do the experiments. So it's not the most effective way of going about this. So there's another method though, and that's called the Buckingham Pi method. And what it does is it basically uses the various variables that exist, and without any experimentation, it can, in a way, shrink the number of variables that affect the experiment. So, for example, how it achieves this is that it creates these things known as dimensionless parameters, and these dimensionless parameters are basically parameters that are made by the combination of the original variables. And so what we try to do is try to find out the different dimensionless parameters that exist in the experiment, and we gather data in for those dimensionless parameters, and we try to find a relationship between these values. So in the case that I just talked about, what happens is we have six different variables, and we find out that there are only three dimensionless parameters that are coming into play in this experiment. So immediately it becomes so much easier to find a correlation between three dimensionless parameters versus six different variables. So let's take a look at the mathematics behind it and get to understand it a little bit better.
So let's start off by making a list of all the variables that we think will matter in a problem like this. So we have water flowing into a tube. So we already know that the density of the fluid is going to matter. And then we have the viscosity of the fluid, and then the diameter of the pipe itself that's going to play a role. And then we also have what exact velocity the fluid is coming in with. And then since sugar is dissolving into the fluid, there's a mass transfer happening there, and there's also a diffusion happening. So we can conclude that the diffusion coefficient is also going to play a role, as well as the mass transfer coefficient. So let's go ahead and make a list of that. All right. So the relevant variables. That's tube diameter, then fluid velocity, and then we have fluid density, and then fluid viscosity, and then mass diffusivity constant, and finally the mass transfer coefficient. So just to make things easier later on, I'm going to represent all of these variables by their symbols. So that's going to be a d for diameter, v for fluid velocity, rho for density, mu for viscosity, dAB for the mass diffusivity constant, and finally Kc for the mass transfer coefficient. So let's go ahead and write down all the units of these variables. And for the Buckingham pi method, we're also going to list all of their dimensions. So let's go ahead and do that. The units, first of all. So the unit of diameter is simply meters. We know that. The velocity is going to be meters per second. Density is going to be kilograms per meters cubed. Viscosity is going to be kilograms per meter per second. And then diffusivity, that's going to be meters squared per second. And finally, the mass transfer coefficient, that's going to be meters per second, same as velocity. So let's go ahead and write down the corresponding dimensions. Meters is simply length. Meters per second is length per unit time. Kilograms per meters cubed, that's going to be mass times mass per unit, length cubed. That's going kilograms per mass per second. That's mass per length per unit time. And then this one's going to be length squared per unit time. And then this one is finally going to be length per unit time. All right, so we have this table. Now what we're going to do is basically make another table, and this time they're going to include all of the dimensions that we have listed here and all of the variables. And we're going to assign each of the variables a unique score based on how many dimensions they have. So what I mean by that is basically, so let's write down variables first. And then we have our dimensions. So let's make a table out of this. Right, so let's take a look here. What are all the different dimensions that we've collected so far? We have length, we have time, and we have mass. I think, yeah, those are the only three variables that we get here. So let's write those down. So here's length, and then mass, and then time. All right, now let's make a list of all the variables that we have again. So we have diameter, we have fluid velocity, then density, diffusivity. My bad, that's not diffusivity, that is viscosity, then the diffusivity constant, and finally the mass transfer coefficient. All right, so what score we're going to assign each of these variables is going to depend on the dimensions that it has. So what I mean by that is, for example, let's take a look at diameter. So the tube diameter only has length in its dimension. So diameter gets a score of 1 for length, 0 for mass, and 0 for time. In the same way, velocity. Velocity has two dimensions. It's length and time. But we need to be careful what power those dimensions have been raised to. So length is raised to the power of 1. So velocity gets a 1 for length. Mass, it doesn't have mass. That means the mass has been raised to a power of 0. So that's going to be a 0. And then finally, time is raised to the power of -1. That's going to be -1 in the score. So in the same way, we're going to construct this entire table. So let's go ahead and do that. So density is 1, that's actually a 0, 1, and a -3. This is going to be -1, 1, -1. Then we have 2 here, 0, -1, 1, 0, -1. Okay, now that we've constructed this whole table, what we're going to do is make a matrix out of this, and that's going to be called our dimensional matrix. So how we do that is basically just keep all the things on the rows in the rows and everything in the columns in the columns. So let's go ahead and construct that matrix. So dimensional matrix dm is going to be equal to, so we have 1, 0, 0. So we're going to write that down as is, 1, 0, 0, and then 1, 0, -1, 1, 0, -1, and in the same way, we're just going to do the entire table. So that's 0, 1, -3, -1, 1, -1. That's 2, 0, -1, 1, 0, -1. Okay. Now that we have the dimensional matrix, what we want to do is calculate the rank of the dimensional matrix. So what is a rank? Rank is basically the total number of independent rows or the total number of independent columns that we have in this matrix. There is a hands-on method of doing this, but for the purposes of this video, we're going to do it in coding. So let's go over and head to Python and try to calculate what the rank of this matrix is. So we just calculated that the rank of the dimensional matrix we had was 3. So what was the point of doing that? Well, basically, the rank of this matrix allows us to find out just how many dimensional groups we're going to have in this situation. So the number of dimensional groups that we actually have is the total number of variables subtracted by the rank of the matrix. So we have 1, 2, 3, 4, 5, 6 variables. We subtract that by 3 and we end up with 3. So we're going to have 3 different dimensional groups. So let's go. I'm going to go ahead and write that. Number of dimensionless groups equals n minus rank, which is 6 minus 3, that is 3. Okay, so we know that we have 3 dimensionless groups, so let's represent that by pi 1, pi 2, and pi 3. So these are our dimensionless parameters. Now, each of these dimensional parameters are going to have what it's called a core group. So what is a core group? So a core group is basically a group of variables that we select from the variables that we already have that we will assign to each of our dimensionless parameters. So the question comes, like, if it's a group of variables, how many variables should we choose? Well, the answer's right here. So whatever the rank of our dimensional group is the number of variables that would be present in our core group. So yeah, in this problem, we're going to have 3 variables present in our core group. So the next question is, well, we have 6 different variables here. Which of these 3 should we choose in our core group? So there's only one rule to do that, and that is all the core groups, the union of all the core groups should contain all of the dimensions that are present here. So that means we have length, time, and mass. So if we need to choose 3 different variables that in their union will have all of these 3 dimensions. So for example, if I select diameter and then fluid velocity and mass transfer coefficient, that cannot be a core group because you see, we have length, time, length, time, but in all three, we don't have a single dimension of mass. So that cannot be used as a core group. Now, let's see, if we use the diameter, the density, and the mass diffusivity, if we'll have all of the dimensions or not. So diameter has got the length, and then from the density we can get the mass, and from diffusivity we can get time. So that group can be used as a core group. Another thing to note, although this is not a rule, is that it's always wise to not keep the variable that we're most interested in our core group. So a mass transfer is happening here. So right here, the variable that we're most interested in is the mass transfer coefficient. So we will not put that in the core group because we don't want this variable appearing in all of our dimensionless groups. We want to isolate it within one of these. So let's go ahead and write down our core group. So that's going to be the mass diffusivity, and then we have our density, and finally the diameter. So let's write that down in all of the dimensionless parameters. Now, we can't just stop at this. We're going to have to raise each of these variables by a different power. So we'll raise the diffusivity here by A, density by B, diameter by C, and the power has to be different in all of these. So this is going to be a D, E, F, not A, B, C, and then G, H, I. Now, the last thing left to do is we take all of the variables that are remaining and we distribute them among these dimensionless groups. So we have velocity remaining. So let's go with V, and then we have viscosity. So that's a mu. And then finally, we have the mass transfer coefficient. There we go. Now, the one thing to remember about these dimensionless groups is that they're dimensionless, which means they don't have units. So using that information, we can actually find out what the value of A, B, C, D, E, F, G, H, I are. So let's go ahead and do that. So our pi1 is equal to diffusivity is, the units of diffusivity is meters squared per second. So that's meters squared divided by second raised to the power of A. And then density. Density is kilograms per meters cubed. So that's kilograms divided by meters cubed raised to the power of B. Diameter is simply meter raised to the power of C, and velocity is meters per unit second. Okay, so you have that. And so let's go ahead and combine all the variables right away. So that's meters is going to be raised to the power of 2a minus 3b plus c plus 1. So that's meter. And then let's take a look at kilogram. For kilogram, we only have 1, so that's going to be kilogram raised to the power of b. And then finally, seconds, that's going to be raised to the power of a and 1. So that's raised to the power of negative a minus 1, because these both are in the denominator, so we'll have to use negative power. Now, since these are dimensionless groups, this should equal 0, this should equal 0, and this should equal 0. So right off the bat, we know that b is going to be equal to 0, and then negative a minus 1 is equal to 0, so that means a is equal to negative 1. And then finally, 2a minus 3b plus c plus 1 should also equal 0. We know that a is equal to negative 1, so that's going to be negative 2. We know b is equal to 0, so that's 0, plus c plus 1 is equal to 0, and therefore we know that c is equal to 1. So we found out what our B, A, and C are. So in the same way, we're going to solve all of this for pi 2 and pi 3 as well. So let's do that. So in this case, these two are like exactly the same. So from there, we can say that B, which is corresponding to H, is equal to 0. And then A, which corresponds to G, should equal -1. And then I, which corresponds to C, should equal 1. So finally, let's erase this part. We have all the values of A, B, C, all the way to I. Now let's write down our actual dimensionless groups. I'll write it down here. So our pi 1 is equal to the diffusivity coefficient raised to the power of -1 and density raised to 0, diameter raised to the power of 1, and velocity. Now, this can be written as Vd divided by dAb. And then our pi 2 is equal to diameter of, my bad, it's actually diffusivity coefficient, density, diameter, mu, and here we're going to raise this to the power of -1, this to the power of e, which is also -1, and finally f, which is equal to 0, and here we get viscosity divided by diffusion coefficient times the density. And finally, our third dimensionless group, that is, so this is going to be raised to the power of -1, density to the power of 0, and diameter to 1. So that is Kc divided by dAb times density. Looks like I made a little mistake here, so diameter should actually be in the numerator for our third dimensionless group because diameter has a power of 1. So yeah, okay. So all of these dimensionless numbers actually have a name to them. So our last one is actually the Sherwood number. Sherwood number, and that's denoted by SH. And this one is actually the Schmidt's number, denoted by SC, and this one is our Pickley number, defined by PE.
Well, now you might be wondering, are these combinations of variables that important that they should get the names of their own? Well, the short answer is yes, because the situation that we just looked at is a very general situation where convective mass transfer is happening. And every time there's a convective mass transfer, where the whole process is always going to be affected by what the diffusion coefficient is, what the mass transfer coefficient is, what the density and viscosity of the fluid is, and even an effective length, which in this case was the diameter of the pipe. So these variables are always going to be present in similar situations. And on top of that, what's going to happen is that more likely than not, you will probably find these variables in these exact combinations, which make up the Sherwood number, the Reynolds number, and the Schmidt's number. So yeah, these variables are very important.
So now let's try and divide the first two dimensionless groups, the Peclet number and the Schmidt's number, and see what result we get. So pi 1 divided by pi 2. Pi 1 is velocity times diameter divided by the mass diffusivity constant, and the pi 2 is viscosity divided by density times the mass diffusivity. Okay, so right off the bat, we see that these two things cancel out, and if we rearrange the variables, that's going to be velocity times diameter times density, all of which is divided by viscosity. Now we know this is actually equal to the Reynolds number. So there we have it.
So now we have a situation where a pure volatile liquid is dripping down the inner walls of a tube, and through this very same tube, a gas is being blown upwards. So now the gas and the liquid are in contact, so the liquid is going to diffuse into the gas, and there's a convective mass transfer going on. So in 1983, Gilliland and Sherwood studied this exact situation with 9 different liquids, and the conclusion they came up with was that the Sherwood number is equal to 0.023 times the Reynolds number raised to the power of 0.83 times the Schmidt's number raised to the power of 0.44. Today what we're going to do is we're going to be using experimental data for the Sherwood's number, Reynolds number, and Schmidt's number, and we're going to try to come up with the same conclusion that Gilliland and Sherwood did. And for this, we're going to be using mathematical methods, namely the Penrose inverse and the sum square difference method. And on top of this, we're also going to be graphically representing our collected data and our model, just to visually see how well our model predicts the observed data.
So to prove the relationship between our Sherwood number, Reynolds number, and Schmidt's number, we're going to first have to start off by assuming that our solution actually takes this form, where Sherwood's number is equal to a constant A multiplied by the Reynolds number raised to the power of B multiplied by the Schmidt's number raised to the power of C. Now, as to how I came up with this equation, there is some theoretical basis for it, but it's beyond the scope of this video, so I'm going to skip over that. You're just going to have to trust me. So once we look at this form, the most natural thing for us to do would be to try to calculate what each of these values are, each of these constants A, B, and C. Because when we do an experiment, we can collect all the variables we'll need in order to calculate our Sherwood's number, Reynolds number, and Schmidt's number, whereas A, B, and C could be any arbitrary number. So let's go ahead and try to calculate those values. First of all, we see that the constants B and C are in the exponents. So the easiest thing for us to do right now would be to take the natural log of on the both sides so that the constants get out of the exponent. So let's go ahead and do that. So that's going to be the natural log of the Schmidt's number equals the natural log of A plus B times the natural log of the Reynolds number plus C times the natural log of the Schmidt's number. Okay, so we're here. Now, when we do an experiment, we're probably going to do it a very large number of times so that we get a better, more accurate result for our equation. So let's assume that for this experiment, we did it 100 times. So we have 100 different values for our Schmidt's number, Reynolds number, and Sherwood number. So in a case like this, I would say doing it as in a matrix form would be the easiest because it takes into account all of the 100 experiments we're going to do. So I'm going to write this down in a matrix form. So let's see what that's going to be like. So I'll go ahead and write the natural log of Sherwood number 1, the natural log of Sherwood number 2, natural log of Sherwood number 3, and this keeps going on and on until 100 Sherwood numbers are done. So that's our one side, and this I'm going to write as
1, 1, 1, the natural log of Reynolds number 1, the natural log of Reynolds number 2, and the natural log of Reynolds number 3. Similarly, it's the natural log of Schmidt's number 1, the natural log of Schmidt's number 2, and the natural log of Schmidt's number 3.
And this keeps going on until 100 values have been down. And then finally, we have natural log of A, then B, and then C. Now, if you look at the right-hand side of the equations, it might look a little bit weird. It definitely looks different from what we have on the second step, but if you do a matrix multiplication of these two matrices, you will end up with that equation because it's simply going to be 1 times natural log of A plus natural log of the Reynolds number times B plus natural log of Schmidt's number times C, which is what we have in the second step. So that's how we represent them in the matrix form. So as I already said, we've done this experiment 100 times. So the dimension of this matrix is going to be 100 by 1 because we're going to have 100 rows and a single column. The dimension of this matrix is going to be 100 rows and 3 columns. So that's 100 by 3. And the dimension of this matrix is going to be 3 by 1. And it's a very small matrix. Now, we have a very weird situation here where we have 100 different equations, but we only have 3 unknowns because Sherwood number, Reynolds number, and Schmidt's number can be calculated from experimental values, whereas these constants cannot. So in normal situations, if we were calculating something theoretical, just solving 3 equations, like picking any 3 equations from the 100 equations, would give you a value for A, B, and C. However, we need to remember that we're finding out these values with experimental data, which is prone to error. So if we only take 3 values and try to calculate A, B, and C, say the equations might be true for Sherwood number 1, but it may not be true for Sherwood number, say, 99. So we have to take into account all of the 100 equations that we just wrote down. So what do we do about it? And the solution is in what we call the Penrose inverse. So in order to do that, I'm going to represent all of these matrices as variables. So let's go ahead and do that. So I'm going to represent our Sherwood numbers by the variable y. And that's our 100 by 1 matrix equal to, now this matrix, which I'm going to call our design matrix, will be represented by X. This is 100 by 3 matrix. And our variables, our unknowns, I will be representing it by the letter B. And that's 3 by 1. So we have this relationship going on. All right, so I've rearranged this equation. I just switched the left-hand side with the right-hand side. So let's see what we can do here. The problem that we're trying to solve is that how we can take all the 100 variables into account to calculate just 3 unknowns. So first of all, let's start by multiplying both of these sides by the transpose of matrix X. A transpose of a matrix is simply the elements on the rows are switched to the columns, and those in the columns are switched to the rows. So the inverse matrix of X sub t, will have the dimension of 3 by 100. So we multiply that on both sides. So we're left with this. It looks like I made a little error here in the dimensions. Okay, so if we multiply these two matrices, the transpose of x and x, what we'll get is a matrix that is 3 by 3. So I'll go ahead and rewrite it. So the transpose of x times x matrix is going to be of dimension 3 by 3. And then we have our variable matrix 3 by 1, which is equal to the transpose of x times the y matrix. Okay, so our end goal is to try to calculate what the value of our unknowns are, and the unknowns are in our matrix B, so it makes sense that we isolate B, like keep matrix B on one side of the equation and keep everything else on the other side. So in order to do that, what I'll do is multiply both sides by the inverse of the matrix, which is the product of matrix X and the transpose of matrix X. So let's do that. So I'm going to multiply both sides by transpose of x times x whole inversed. And this is also going to be a 3 by 3 matrix. So let's go ahead and put that there as well. That's transpose of x times x raised to the power of -1, 3 by 3. Now, we know that any matrix multiplied by its inverse is equal to the identity matrix. And the identity matrix multiplied by another matrix is always equal to the other matrix. Okay, so the result of this whole left-hand side is simply going to be the matrix B. And what we have left on the other side is the transpose of matrix X times X inverse times the transpose of X times the matrix Y. So this relationship is what we obtain from our Penrose inverse. So we can see that the transpose of matrix X is 100 by 3. The matrix X itself is also 100 by 3. And Y matrix is 100 by 1. So we can see that all the 100 values that we collected in our experiment have been taken into account to find the 3 unknowns that we have in matrix B. So that's how we're going to use Penrose inverse in order to find our constants A, B, and C. We are not going to do that on the board. We're going to code that out in Python. And so let's see what values we get for A, B, and C. All right, so now we're in Python, and now we're going to try to solve the Penrose inverse in order to find what the actual values of our constant A, B, and C are going to be. So first of all, in order to do this, I'm going to have to import the NumPy library. So let's go ahead and do that. I will import it as np. There you go. Now, in order to solve this actual problem, I'm going to have to feed some data into it. I have this data copied in my clipboard, and I'm just going to paste it and run it. I am not going to explain how this data was calculated because it's just going to cause some confusion right now. So once I've solved this entire problem, I'm going to go back to this line, cell 2, and explain how exactly I got that data from. But for now, just trust me, that's a good data. So the next step. As we can see from the Penrose inverse equation that I wrote down there, we need to input what our cells, our matrices X, Y, and B are going to be. So first of all, let's write down what our matrix X is going to be. So X has 3 different columns. The first column has nothing but 1. The second column has all the Reynolds numbers, whereas the third column has all the Schmidt numbers. So let's write that in a parentheses before I declare a variable for it. So the first one is just an array, should just be an array of the number 1. So what I'm going to do is np dot ones underscore like re. So what this line exactly does is that it makes an array of only the number 1, but this array is going to be identical, not identical. So what it's going to do is basically it's going to take my array of Reynolds numbers, and it's going to replace every single number in that array by the number 1. So let's see what I exactly mean by that. So first of all, let's see what my Reynolds number is going to be. So these are my 100 values for the Reynolds number, and if I do np dot ones underscore like Reynolds number, what I get is this array. So basically every single number in the Reynolds number array has been replaced by 1. So that is the first column that we need. Our second column is basically the natural log of all the Reynolds numbers. So that's going to be np.log of our Reynolds numbers. And finally, on the third column, we have the natural log of the Schmidt number. So that's going to be np.log, natural log of the Schmidt number. So yeah, these are the 3 things that we need for our matrix X. Since these 3 items are stacked in a column, what I'm going to do is, let's enclose this in large brackets because we want an array, and then within parentheses. So what I'm going to do is np dot column stack. So basically what this is going to do is it's going to put all of these 3 things in 1 column each. So let's run this code and see what it looks like. So there it is. So all the 1 is in 1 column, all my Reynolds numbers are in another column, and all my Schmidt numbers are in the final column. So that I will be storing in the variable x. There we have it. And so what do we do for y? So we can see that our matrix y is basically the natural log of all of our Sherwood numbers. So that's y is basically going to be the np dot natural log of the Sherwood numbers. So we have our x and y. Now, our matrix B that we need to calculate is written out right there. So first of all, we need to find out what the transpose of matrix X is going to be. It's fairly easy to transpose a matrix in Python. What you basically do is take the matrix and write down dot uppercase T, and it just transposes our matrix for us. So that's our X transpose T. Now we need to also find what the product of the transpose of X and X is going to be. So this is going to be a matrix multiplication, so we can't simply just type x dot t times x. This is not going to work because it's a matrix and we're doing an algebraic multiplication here. So in order to do a matrix multiplication, we simply replace the multiply sign by and at the rate. So that's going to give us our 3 by 3 matrix that we talked about earlier. So we have that. The next step is to find the actual inverse of this whole multiplication. Now, the way to do this in Python is basically typing np.linalg for linear algebra .inv for inverse. So the inverse of our multiplication is basically this result that we just got. So if we matrix multiply this inverse by the transpose of tx and multiply that by the y matrix, we're basically going to get our matrix B, which is what we've been looking for all along, because matrix B has our A, B, and C. So right off the bat, we can see that the value of the constant B is 8.3609 and C is 0.3943. And what we're gonna do, the value of A is not negative 3.79 because the first element of our array, of our matrix B, is actually the natural log of A, not A. So in order to calculate it, we're basically going to have to find the exponent of this number right here. So in order to do that, I'm going to store this whole array in the variable B. And now my variable A is going to, now constant A is going to equal np.exp. Basically, I'm raising this by the power of E. No, I'm raising E raised to the power of the first element of the array B. And since we're already here, let's store the second value in the variable lowercase b and the third value in the variable up lowercase c. So that's B1. So there we have it. So our variable A is equal to, our constant A is equal to 0.022, which is almost equal to the answer that we want, which is 0.023. And then our variable B is equal to, it looks like I made a little mistake here. So it should be 1 here and 2 there. My bad. Okay, so let's see what our variable B looks like. Our constant B is equal to 0.836, which is very close to 0.83, the actual value that we need. And then our variable C is equal to 0.39. This is also very close to the value of 0.44 that we need. So yeah, so by this method, we can calculate A, B, and C. Now, as I promised, I need to explain the second cell of this whole script. So what I basically did here is that for the Reynolds number, I created an array of random values. So let's look at how I did that. I did np.random.uniform. This basically makes an array of random values, random uniform values. And the range for the array I gave it was 2000 being the minimum number and the maximum number being 35,000. And I wanted 100 values inside my array. So that's how I created my Reynolds number. So this, something like this would be my Reynolds number. Since this is randomly generated, the Reynolds number that I got here may not be the same as I got here, because every time I run this line of code, the Reynolds number is going to change. For example, we have 20,156 right now. If I run this code again, yeah, that's changes to 19,516. So yeah, that's how I got the Reynolds number. For the Schmitz number, it's basically the same idea, except the range has been changed. It's been changed from 0.6 to 2.5 instead of 2,000 to 35,000. Now, after this, what I did is that I actually used the equation that we have itself in order to calculate the Schmitz number based on the two random values of Reynolds number and Schmitz number that we got. So I pretty much just calculated what the Sherwood number would be based on the random values of Reynolds number and Schmitz number. And then what I did was okay, let me do this part once more time. So what I did was np.random.normal. So this means I'm trying to create a normal distribution. And my normal distribution has mean, LOC, location, which means mean, the center of the normal distribution, at the Sherwood number, the calculated Sherwood number, the number that we just calculated right here. So that, and scale at 10% of the Sherwood number that we calculated. So what this means is that I took the original Sherwood number and I made a normal distribution out of it, and I introduced an error of 10% within those values. So what this line of code does is basically it generates a random set of values based on my originally calculated Sherwood number, and and it makes it randomly distributed such that there's a 10% error in all of these values. So yeah, it sounds like something that's extremely stupid to do because we're using the actual equation to make a experimental data, and we're using that to prove that the original equation is true. So yeah, it sounds stupid, but in reality, this is pretty much how it works. Because like if we were to go out in the real world and do this experiment, you would get a normal distribution of values that are based on our equation right there with some percentage error. So that's basically how I did that. So yeah, this is one way to uh, explain this equation right here. And yeah. So the second way that we can find out what the values for our unknown constants A, B, and C are is what's called a sum squared difference method. So what do I mean by that? So we have our actual equation, which we assume to be true. And what we want to do is see if our observed value, how different our observed value is from a calculated value. So what we're going to do for that is make a guess for A, B, and C, and then we're going to try to calculate the right-hand side of the equation, since we already know what the Reynolds number and Schmidt's number are going to be from our experimentation. And we're going to subtract that from the Sherwood number that we also got from the experiment, and we're going to see what the difference between those are. And we're going to make multiple guesses for it, and then we're going to see which combination of A, B, and C gives us the minimum possible value of the difference between the left-hand side and right-hand side of the equation. So let's go a little bit more in depth about this method. So right here, I have a simple two-dimensional graph with two variables, x and y. The line that's going right through the points are our observed values. So we directly did an experiment and found both x and y to go on a line like this. And the axes that you see on the graph are what we got by making a guess for A and B. For example, I assumed A to be, say, 0.1 and B to be 0.03. And using that, I took a value of x from our experiment and then calculated this value, only the right-hand side of the equation. And then I plotted whatever the answer from that calculation was. I did not use the observed value of y, so keep that in mind. So I got all these different points along the graph. Now you can see that these points don't exactly align with our observed values, which is the line. So what we do from there is see how each of these points are different from the observed values. So for the first point, this distance right here would be the difference between the observed value and the calculated value. So what we could do from there is add up every single one of these differences. So all of these differences are what we calculate. So once we have all of those differences, we add them up to get a total error. So now you guys might see a problem here because we have an error that's larger than the observed value and some error that are smaller than the observed value. So if we just subtract the observed minus calculated and add all of them up for all of these points, we're not going to get a total true error because some errors are actually negative, and those are going to actually subtract from the total error. So we don't want that happening because our calculated number being smaller than the observed number is just as bad as our calculated number being larger than the observed number. So what we want to do in this case is that we'll take the difference, square it. So if it has a positive sign, for example, if this one had a +1 error and this one had a -1 error, we're going to square every single one of these. So this error squared becomes 1, and this error squared also becomes 1. So that gets rid of our problem where negative error was actually taking away from the total error. So now we have a positive value for every single one of these errors, and then we add those errors up and end up with a total error. So that's after our first guess. After this, we make another guess, and we can make as many guesses as we want. And finally, what we want to do is like choose the smallest total error from all of those guesses that we made. So yeah, that's how sum square difference method works. So right here, how I would write that is that we take the observed value of the Sherwood number, subtract it from the calculated value, which is A times Reynolds number raised to the power of B times Schmidt's number raised to the power of C. We subtract that, and then we square the entire thing, and we add every single one of the data points up. So we're gonna perform this exact calculation on every single one of the data points we have. So I starting from 1 to all the way to n, and we're going to do this for numerous different values of A, B, and C, and numerous different combinations of it. And once we have all of those points, we're going to minimize this whole value, which means we're going to try to find the smallest one of those values, and whatever gives us the smallest value is going to be assumed to be the actual value of A, B, and C. So the reason we're actually only minimizing this error and not going for 0 is that all of these values for Sherwood number, Reynolds number, and Schmidt's number are obtained by experimentation, and these are prone to error. So theoretically speaking, this number can go to 0, but in the real world, errors can happen, and it's better to just go for the smallest error than to absolutely look for a 0, because that is very unlikely to happen. So yeah, that's the sum square difference method. Now we're going to go ahead and do all of this in Python. So now let's go ahead and calculate our values for our constants A, B, and C with the sum square difference method. So we just calculated that the equation on the board is what we need to solve in order to use that method. So let's go ahead and write our equation in Python first. So in general terms, what do we need? We need the Sherwood number, and we want to subtract that by our constant A multiplied by the Reynolds number raised to the power of B, and multiplied by the Schmidt's number raised to the power of C. And we want to raise this whole thing by the power of 2. We need to square the whole differences. So, and after we've done this, we want to do this for every single value, corresponding values of the Reynolds number, Schmidt's number, and the Sherwood number. And the way to do this is basically, let me put this all in parentheses, and what we can do is np.sum, easy as that. So this single line of code is basically going to add every single result from the corresponding values of Schmidt's, Reynolds, and Sherwood numbers. So obviously we can't just go ahead and use it like this because we haven't defined A, and we still need to figure out how we're going to find the minimum value of all of these sums. So I'm not going to execute this line of code. I'll just open another cell and let's see. The way to actually find the minimum from a certain amount of values is using the SciPy optimize minimize function. So let's go ahead and import the minimize function first. So I'm going to say from scipy.optimize. I spelled that wrong. Optimize import minimize. So we need this particular function in order to minimize the function. So let's go ahead and try to use that function. So what does it say? Minimize brackets. So first of all, it tells me that it needs a function in order to execute, and it needs initial arguments, initial guesses. So let's go ahead and make our function first. So I'm going to turn this cell into a function. So let's define, I'm going to call my function SSD for sum square difference, and it's going to take the variable p as input. And what I want the p to do is basically I will feed the initial guesses for a, b, and c into the p as an array. So the first element in the array will be a, the second one will be b, and the third one will be c. So by that logic, I'm going to have to replace a by p, first element of p, and b is replaced by the second element of p, and c is replaced by the third element of c. So, and this is pretty much the only thing we want this function to return, so I'll just keep the statement in the return statement. So yeah, that's the function we need. And now for minimize, we're going to feed it our function, which is SSD, and then our initial guesses, let's just say 3, 1, and 0.5. So let's run this thing. Okay, so it ran into an overflow, so I'm just going to make the guess. I'm just going to make a better guess. So this is basically telling me that my guess is not good enough. So let's go with 1, 1.5. Okay, there we have it. So our minimized values are basically right there. So for A, we got a value of x0. For B, so actually let me call this let me store this into the variable of what should I call it? Let's say min. Let me store it there. So A is going to take the first element from the array of x from within the object min. So that's that, and let's give this the second value, and then let's give C the third value. Alright, so for A we got 0.31, which is, I'd say it's pretty close to 0.23. For B we got 0.79, which is also pretty close to 0.83. And for C we get 0.42, which is also very close to 0.44. So that's how we use the sum square method to calculate the value of the three constants. Now, there's another method of doing this, which is also a part of sum square method, except that we use a very different equation. Specifically, the equation that we got by putting log on both sides of the main equation. So let's go ahead and try to do that as well. So what I mean by that is that we have this particular equation which we made by taking a log on both sides of this equation as well. And we might as well use this and in order to calculate the sum square difference. So if we're trying to do that, the sum square difference would look something like this. So it's going to be the summation from I equals 1 to n, and our left-hand side of the equation is the natural log of here. This number, the Sherwood number, the natural log of Sherwood number minus the right-hand side of the equation, which is natural log of A plus B times natural log of the Reynolds number plus C times the natural log of Schmidt's number. And we square the whole entire thing. So we can do this. We can use this equation in order to calculate the sum square difference as well. So, well, which one of these two should we do? Well, one might assume that it's the exact same thing, but it actually isn't. So, and let me explain exactly why. So let me erase all of this. So most of the times in engineering, we have two different kinds of measurements. One with absolute error and the other with relative or percent error. And let's see what their graphs are going to look like. So for the one with absolute error, we would have like points like this going all the way in the graph, and their error bars would look something like this. Yeah, so their error bars would look pretty much constant. And this is the graph for absolute error. Whereas for relative error, our graph is going to look like this. Yeah, so this one is for relative error. So yeah, whenever there's a percent error in an instrument, error is going to look like this. So at first, there's a very small error in the magnitude, and as the value, measured value gets larger, the error gets larger as well. Yeah, so absolute error usually occurs when you're measuring something in a very short range, and you're using the same instrument to measure those measurements. So for example, like in a lab, you're trying to measure the mass of a powder, you would use a scale, and which is accurate to 4 decimal places. So in cases like that, the error would look pretty much constant. Whereas on the other hand, relative error occurs when you're measuring measurements in a wide range and you're using different kinds of instruments to measure that. So for example, you're trying to measure the weight of many different kinds of things, not just something in a lab. So if you want to measure something like the weight of a coin, you'd probably use a scale that is accurate to 4 decimal places, like the ones you get in the lab. And then maybe if you want to weigh vegetables, you'll probably use something that's accurate to 2 decimal places. And then let's say you want to measure the weight of a person. You'd probably use something more accurate to 1 decimal place. And then let's say you can want to measure the weight of something like a truck. You'd use an entirely different instrument for each one of these cases. And all of them have a percent error. And since the mass gets larger, the error values also get larger. So in cases like where we see relative error, and this is a lot more common in engineering situations than the absolute error. So every time you have an absolute error, you want to use the log graph. You want to convert this graph into a logarithmic graph instead. And what that does is it converts this into a graph that looks like that, which is what we want. We always want our graph to have error that looks like this in order to do our sum square difference. On the other hand, if you have absolute error and you try to convert this into a logarithmic graph, this is going to look, the error bars are going to look something like this. So right. So as you can see, the error bars are significant at first, but they keep on going to be smaller and smaller and smaller until the error doesn't exist at all. And that is not what we want. We want to actually measure how much an error is affecting the calculations. That's the whole point of doing the sum square difference. If we convert this into a log graph, it's going to minimize the effect that the error has on the calculated value. So we're not supposed to convert this into a log graph whenever we have an absolute error. So in our case, where we're looking at the Reynolds number that range all the way from 2,000 to 35,000, which is a relatively large scale, we can say that we have relative error in our measurements. So it would be safe to use log transformation in our data and then try to calculate the sum squared difference in order to find the values of A, B, and C. So let's head back to Python one more time and try to calculate it that way.
So now that we know that a log transformation fits our data better, all that's left to do is convert everything we've already done into a log format. So we have our main equation right here, so we can see that we need to convert the Sherwood's number into a natural log of the Sherwood number. So let's do that. And we'll leave the p's as is because we're going to feed the data in anyways. We just have to change a little bit what the data we're feeding in actually is. Yeah, so this p0 is a, and we actually want the log transformation of a as well. So let's do that. np dot natural log of a, and it's going to be plus our, actually I'm just going to delete this whole thing. Let's just type out the whole equation one more time. So what we have is the log transformation of our Sherwood number minus the log transformation of A. Let's put this thing in brackets. Okay, so we add B times the natural log of our Reynolds number plus C times, again, the natural log of our Schmidt's number. So we've already established that A is going to be the first element of the array of P. Our B is going to be the second element, so that's P1. And finally, C is going to be our third element, so that's P2. Right, let's execute that. Okay, looks like there's an error here. Let's see what mistake we've made. Expected after parsing. Looks like I might not have enough parentheses. Okay, I think that solved the problem. Alright, there we go.
Okay, it looks like I forgot to add the square right here, so let's go ahead and add that. Double asterisk 2, and if I execute that, and then that, and finally we have the three values for A, B, and C. So our value of A looks like it's going to be 0.023227, that's almost 0.023 that we needed. And another the value of B is 0.83, and that's right on the point. And then our third value is going to be 0.425, which is very close to the actual value of 0.44 that we needed. So I'll go ahead and store all of those as well. A is equal to, yeah, another mistake. So let's go ahead and store this in min again. Execute that, and then we have 0.023 for A, 0.83 for B, and 0.43 for C. So yeah, that's basically how we prove using sum square difference while doing a log transformation to calculate the values of A, B, and C in the equation. Now, all that's left to do for us is pretty much graph the equation and we will be done. So let's go ahead and do that. So now that we have all of the data that we need, it's time to plot the graph and see what it looks like. So first of all, in order to draw the graph, we're going to need to import some libraries. So I'm going to import plotly underscore subplots as, oh, that was a mistake. So I'm going to import from plotly under dot subplots, import make underscore subplots. And then I'm going to import plotly dot graph underscore objects as geo, and I'm also going to import plotly.io as PIO, and finally I'm going to make my graph into dark mode, so that is PIO plot, I'm sorry, it's PIO dot templates dot default equals quotation mark plotly underscore dark. So we go ahead and run that. Everything's imported. Now, first of all, we make our canvas for our graph. So that'll be created as an object. So that's fig. I'm going to name this as fig, and that's going to be equal to make underscore subplots parentheses and okay, parentheses enter. So for the graph, I'm going to add fig dot add underscore traces. I think I made a mistake here. Fig dot add. Okay, add underscore traces, and I'm going to go type graph objects dot scatter 3D. This is going to enable me to make a 3D graph for our plotting purposes. And here in the x-axis, I'm going to put the Reynolds number. In the y-axis, I'll put the Schmitz number, and on the z-axis, I'll be putting the and on the z-axis, I'm going to put the Sherwood number. So let's go ahead and see what that looks like. It looks like we have quite the mess of a graph. So let's just clean this up a little bit. So what I'm going to do first of all is get rid of all these lines. So I'm going to put the mode. So I'm going to set the mode to markers. This is going to get rid of all of the lines. And I'm going to set the marker size to 3 so that the dots don't look as big as they do right now. And I'm also going to change the marker color to SH. It's going to make this graph a little bit more colorful. It's going to look a little bit prettier. So let's see what that looks like. Okay, looks like I've come across an error. Okay, there's something wrong with the marker size. All right, it looks like I made a spelling mistake here, so it's marker size, not maker size. So let's see what that looks like. All right, there we have it. That looks a lot better. I'm still going to make a few more adjustments here. Let's go with fig.update underscore layout. And here I'm going to say width, set the width to 800 and height to 800 as well. So, so that this graph doesn't occupy the entire all of my screen. It just stays on the left side of my screen and it looks bigger. And what we're also going to do is label all of our axes. So for that, we're going to do scene equals dict, and that's x-axis underscore title. Just going to copy that, is equal to RE because we have Reynolds number in the x-axis, and the y-axis title will be Schmidt's number, and finally the z-axis label title is going to be the Sherwood number. So let's go ahead and see what that looks like. All right, we have all of our labels and our graph looks bigger and it stays to one side. All right, so that's our representation of the data points that we actually got. Now, what we also want to do is graphically represent just how well our data model fits these observed data values. So let's talk about how we're going to do that. So now that we have all of our data points and we've plotted it in a graph, all that's left to do is graphically represent just how well our model actually fits our observed data. So how should we go about doing this? So normally in a two-dimensional graph, what we would do is we would draw a line of best fit, but here we're working with a three-dimensional graph. So what we'll instead be comparing it with would be a plane of best fit. Today we won't be drawing an actual plane, but we will be drawing a mesh, which is pretty much a plane if you look at it that way. But anyways, to explain how we can draw a mesh for our model, let's take a look at a simpler two-dimensional example. So here we have a graph, a two-dimensional graph, and say we know that all of our data fits between 1 to 4 in both x and y axis. So let's draw that right now. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so let's first draw a grid from 1 to 4 in both x and y axis to represent the area in which all of our data fits into. So we have this. Let's make that a bit more straight. All right. So this is a little bit of what we're trying to do with our three-dimensional graph. So in order to get a grid like this, one way to do it would be making a table of values for each of the coordinates of the intersection of this in this grid. So right now I drew these lines arbitrarily, but this can be done by selecting very specific points. For example, I could choose 1, 2, only 1, 2, 3, and 4 in the x-axis as well as the y-axis. So let's go ahead and make a table of what that looks like. So I've got x-axis in the vertical part of the table. So in the rows, we have x-axis. That's 1, 2, 3, and 4. And on the horizontal axis, we have the x-axis. So that's 1, 2, 3, and 4. All right. Okay. So we have this table. Now I'm going to just match these two coordinates and match these 2 points and make coordinates out of them. So 1 and 1, 1 and 1 would be 1 comma 1, 1 and 2 would be 1 comma 2, 1 and 3 would be 1 comma 3, and finally 1 and 4 becomes 1 comma 4. And in the same way, we'll complete the entire table.
2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3.
Okay, so these are the coordinates we've got. So if we were to plot each and every one of these coordinates, we'd pretty much get this grid. So let's take a look. We have 1 comma 1, which is right here. And then we have 1 comma 2, that's right there. 1 comma 3 is right there, and 1 comma 4 is right there. Similarly, let's take any one point, like 3 comma 3. Our 3 comma 3 is right here. So basically, using all of these coordinates, we can draw out a grid. Now, for a second, let's imagine that this is not any random two-dimensional graph, but this is the graph that we're actually working with a z-axis right there, and here we have our Reynolds number, and we have Schmidt's number and the y-axis, and so we'll have the Sherwood number in the z-axis. So let's switch that around as well. We have Reynolds number and Schmidt's number. Now, in order to draw our grid, all that we need to do, the only change we need to make here is that we need to use all of these values and calculate the corresponding Sherwood numbers. And once we have those, we will get a 3-point coordinate, and we can plot those in our three-dimensional graph. And by making a line of those graphs, we can pretty much make a three-dimensional mesh that will properly model our data. So let's go ahead and try to do that in Python. So in order to graph our mesh, we're going to need to get our coordinates first. So before we head into this problem directly, I'm going to take a look at a more simpler problem. Let's try to make a coordinates out of the values that I've got right here in the table. So first of all, I've got, let's call this x, which is going to be equal to 1, 2, 3. So let's make an array of 1, 2, 3. There we go. And then we have y, which is going to be equal to the array of a, b, and c. A, b, and c. Okay, we have these two arrays. Now, what I want to do is create ordered pairs like the ones you can see in this table in the board right now. So let's go ahead and make that. So that's going to be, to do that, we're going to have to write this line of code. So np dot mesh grid of x comma y, and it's going to give us this very weird result of two different arrays. So we're going to go ahead and store that into two different variables. So let's call the first one x grid and the second one y grid, xg comma yg, and we store that and you store the results of these into the two different variables. There we have that. So let's see what xg looks like. So that's our xg, 1, 2, 3, 1, 2, 3, 1, 2, 3. You can see on this side of the board that we've got 1, 2, 3, 1, 2, 3, 1, 2, 3, 2. So yeah, so basically where that comes from is here, like we've got A1, A2, A3. So on the first row, we've got 1, 2, and 3. On the second row, we've got B1, B2, B3. So that's 1, 2, 3 again. On the third row as well, we've got C1, C2, and C3. That's 1, 2, 3 again. So that's what it's about. We've got 1, 2, 3 in 3 rows. Similarly, let's take a look at what YG looks like. And it's just 3 A's on the first row, 3 B's on the second row, and 3 C's on the third row. And that's exactly what we have on our board as well. So all that's left to do is pair these values to each other. So the way we do that is we do a type for I comma j in xg comma yg, and we print out the result from I and j. Print I comma j. I forgot an important thing here. We need to zip these two arrays together. What zip does is basically it just corresponds the first element from an array to the first element of the second array. So it just pairs up the two values. So let's see what that looks like now. So and there we have it. The 1, 2, 3 got paired with A, 1, 2, and then with B, and then with C. So using this, we can plot out all of these values on a graph to get an actual grid. So let's see what this would look like in our problem. Let me go ahead and delete all of these first. All right. So within the graph, it's within this cell where we're actually graphing things out. Let me do all the calculations right there. So first of all, for the grid from Reynolds number and Sherwood's number, I'm sorry, for Reynolds number and Schmidt's number, let's call them RE grid and SC grid. That will be equal to NP dot mesh grid. This is simply the way to make a mesh grid like we just did. So the first element for the mesh grid will be the default values for the Reynolds number, and that's np dot linspace. For the standard default values for the Reynolds number, we're just going to make an array of linearly spaced values from 2,000 to 35,000, and we're going to make 15 different values of that. So I'm going to type that out. That's going to be 2e3 comma 35e3 comma 15. And for the values for the Schmidt's number, we're also going to make a linearly spaced 15 values ranging from 0.6 to 2.5. So that's np dot linspace 0.6 comma 2.5, and we need 15 of those values. So we have our mesh grid right there. And as I've already stated, for the Sherwood number, we're simply going to calculate the actual values from the corresponding Reynolds number and Schmidt's number. So writing that down in code, sh grid would be equal to A, which we calculated, times RE grid raised to the power of B, which we also calculated, times the Schmidt's number in the grid raised to the power of C, which we also calculated. So we have all the necessary values in order to make our mesh. Now it's all that's left is to graph it out. Okay, so what we need to do now is, again, pair up the three values so that we have a a bunch of ordered pairs. So in order to do that, we use the zip function one more time. So that's for I, J, K in RE grid, Schmidt's number grid, and Sherwood's number grid. And here what we're going to do is directly add these into the figure. So that's fig.add underscore traces. And on the x-axis, we're going to put in I because it corresponds to the Reynolds number. Oh, I forgot to zip this thing again, so never forget to zip. And on the y-axis, we're going to put J, which corresponds to the Schmidt's number, and on the z-axis, we're finally going to put the Sherwood number, which is corresponding to K. So let's see what that looks like in our figure. All right, it looks like I have made an error here. So let's see what went wrong. Expected argument X. Okay, I see. It looks like I forgot to specify what kind of graph I want here, so let's go ahead and fix that. That's go.scatter 3D. See if that works. Okay, still doesn't work. Let's see what went wrong here. Okay, another typo, 3 T's. Okay, there we go. Now it did work, but this is definitely something that we don't want. We just want a line, not the whole bunch of dots that just cover up our observed values. So let's go ahead and fix that. I'm going to change these dots into lines. So what I'm going to do is comma, set the mode to just only lines. Let's see if that fixes it. All right, that's looking much better. But what I'd like to do now is just make the lines more monochrome because our dots are already colorful. If the lines are also colorful, they're just going to clash together and nothing's going to be very visible, and we don't want that. So let's change the color of those lines. So line underscore color and set that to gray. And that's looking much better. Okay, so we made the lines on one direction. Now we want to make these lines on the other direction as well, perpendicular to these lines that have already been created. So it's pretty easy to do. All we need to do is switch around the Reynolds number and Schmidt's number. So I'll just pretty much just copy and paste everything. All right, copy and paste, and we just switch places between these. So Reynolds number becomes Schmidt's number, and Schmidt's number becomes Reynolds number. Same thing here, we just swap out these two. And we should be good to go now. So let's see what that looks like. All right, so we have our mesh. So one last thing that I'd like to do is get rid of all of these legends. Like these 40 different legends are way too many for this graph, so I'm just going to get rid of all of them. So for that, I'm going to come down in the bottom line of the code and write down show legend equals false. That's going to get rid of all of the legends. All right, perfect. So this is where we want it to be, and we can see that our model, which is represented by the mesh, is pretty close to the observed value that we got. So yeah, that's the representation of everything we've done so far.
So today we learned about the Buckingham Pi method, which enables us to find out these dimensionless groups, which make it easier for us to find relationship between the variables when there are far too many variables involved in a particular scenario. We also learned about the various mathematical methods, namely the Penrose inverse and the sum squared difference, in order to predict a model out of observed data. So I hope you guys learned something important today, and I will see you guys on the next one. Bye bye.